In this class we will discuss about berm breakwater. The berm breakwater, unlike conventional breakwater, there is a berm, this is called as a berm. So we will discuss about this in this class. We are going to discuss about two types of breakwaters with two different stability numbers. One is reshaped breakwater, another is non-reshaped breakwater. So the difference between them is the stability number 1.7 and 3. I will just give the berm breakwater. The sample design calculation. The water depth is 0.8 meter. Some of the procedure is same as conventional breakwater. You calculate the maximum wave height 0.78 d. This wave 6.24 meter what we are talking is the wave which is non-breaking. Suppose you have the wave and you have this water depth. The stability number what we are talking is different for a breaking wave and a non-breaking wave. There are two approaches for wave breaking, that is h by d should not be greater than 0.78, h by d should not be greater than 0.14 tan h k d. So if it is greater then it will break. Then one of the classes I said for 100-year return period if the wave height is let us say for this case 6.5 meter and this maximum wave is 6.24 meters the wave height. Suppose when you go to the coast the water level will go on decreasing. You take a water depth of 5 meter, then what will be your x max? X max will be 0.78 into 5. So this is 3.9 meter. I am going to ask a question. The 6.24 meter is to be considered as a breaking wave or a non-breaking wave, whether this 3.9 meter is to be considered as a breaking wave or a non-breaking wave. Question is not clear. The answer is the same for both the cases of 8 meter and 5 meter. Whatever wave heights you are getting by using this formula, h breaking wave is h by d is equal to 0.78, then we have to calculate this you have to assume these waves as breaking waves, and the stability coefficient k d for breaking wave it is 2, for non-breaking wave it may be between 3 to 4. If the 100-year return period wave height is 6.5 meter, if you go for water depth more than 10 meter, for 10 meter what will be the wave height? H max will be 0.78 into 10, that is 7.8 meter. Suppose you go to a deeper water, I will go to the other side of the boat, then here the water depth is 10 meter, here the breaking wave is 7.8 meter, but in this case you should consider only 100-year return period wave of 6.5 meter, you should not consider 7.8 meter. See, in a 100-year return period your waves of 6.5 meter only will come, right. A 6.5 meter when it is travelling here, when it comes to 8 meter water depth it will break. If a wave of 4 meter comes, it will come and break at 5 meter, but at this location the wave of 7.8 meter or slightly more has to come to break, but wave of 7.8 meter will not come, then it will not break, then we have to use 100-year return period wave of 6.5 meter. Is it clear that there should be a wave for this particular site at Gopalpur, 100-year return period wave is 6.5 meter. The 6.5 meter wave when it comes, it will break in water depths of about 8 meters. A lesser wave of 4 meter comes, it will break in a water depth of 5 meters. It can come anytime, 6.5 come and less than 6.5 also will come, but there may not be any wave which will be coming more than 7.8 meter. When more than 7.8 meter comes only the waves will break, otherwise what we have to assume is we should not assume this, we should assume only 6.5 meter non breaking wave which can have a higher stability coefficient, and that a case your weight of the stone will be less compared to a breaking wave. So, this is the influence of breaking wave on design of breakwater. I am going to ask this question, if you have any doubt you ask me, all of you it is clear. Suppose not clear, what is not clear you have to tell, then only I can tell. You know what is a return period design wave? What is the design wave? How the waves are formed? How is the wave formed? Because of wind action. So, you need for a wind to have sufficient duration and fetch. Fetch means the area over which the wind is acting, and duration means number of hours the wind is acting. So, based on that you will have the wave height which is generated. For 100-year return period, that is over a period of 100 years, if you take, the maximum wave which can be produced is 6.5 meter. Suppose 6.5 meter waves come in 10 meter water depth, will it break? No. It will not break. So, we cannot use the breaking wave height at 10 meter water depth, we have to use only 6.5 meter non breaking wave for the design of breakwater, because 7.8 meter wave will not come. So, you have to use this statistical information.
Why did you choose 100?
What do you want to choose? You tell me what is.
Why 100? If
I am asking you what do you want to choose.
If you would have taken 1000, it may have been greater than 7.8.
You can use 10 also, 25 years also. But 100 is a round number, they have used it. There is a basis for that. The basis is generally you have to discuss about the life of the structure. You are from civil engineering or which branch? Huh?
Yes.
Civil. What is the design life of a structure? Not correct. This is a very interesting topic, I will not spend time on that. The design life of a marine structure is between 40 to 60 years, onshore structure is 60 to 75 years, this is what is happening. In Singapore we have to consider design life is much less, because every 10th year they demolish the structure and reconstruct the structure. This is a different aspect. Design life depends on the durability of the structure, durability is about the corrosion and other aspects. Other thing is reclassification of structures. Suppose if you are coming after 20 years to Chennai, you will be seeing at some places what was existing earlier will be totally different now, because the zones are reclass. The typical example is the OMR road in Chennai, where some 20 years back all villages, huts and all, now you have Hiranandani and all kinds of flats. That is what they are building because of the necessity of urbanization. In Singapore, every 10th year or 15th year they demolish the structure and then reconstruct it. Except the heritage structures, we have so many kingdoms, Chola, Chera kingdom, Pandya kingdom and all. None of the palaces you will be able to see, only temples we are seeing, because temples are designed for with higher factor of safety and the design life is much more than normal residential building and palaces. So the 100-year is taken because twice the design life is considered as the life for which you have to design. There the fatigue comes into picture. When you talk about the life of the structure, it is the fatigue design which controls. The fatigue design life will be twice the design life of the structure, that is why this 100-year comes into picture. So after 100 years the structure will not be safe, because there will be so many storms it will be taking place, there will be some damages which will take place. So you have to strengthen the structure after 100 years. That is the reason why we take the 100 years. But to fix the top level of the structure, I said we have to take 1000 years return period wave, because in Katrina in US Gulf of Mexico, when Katrina come, the top level was much higher than 100-year wave. Because of that the top of the jacket platform was damaged. So for that reason they want to fix the top level considering 1 in 1000 year. Suppose you want to build an atomic power plant, you want it to be very safe, you can take 1 in 10,000 years. There is no limit for this, it depends on what is that you are designing, what is the importance which you are attaching.
The design wave at 5 meter depth is 3.9 meters.
Because that is a breaking wave. Yes, a 6.5 meter comes, it will break at this location. A 4 meter wave when it comes here, it will not break. You have to take the 4 meter as a non-breaking wave. It will travel here and goes to this place and it will break at 5 meter water depth. So you have to take this as a breaking wave. The stability coefficient in Hudson formula is different for breaking wave and non-breaking wave. So breaking wave needs higher design. So another important parameter is this breaking, this is a significant wave height for which we are going to design. Similarly, when you talk about the stone, the size of the stone is written as W50. So soil mechanics, we know what is D50. Do you know what is D50? All of you might have completed soil mechanics course. You would have done a laboratory sieve analysis. You have done sieve analysis. Sieve analysis you have done or not? Sieve analysis means in houses, the housemaid earlier days they used that jalladai to separate the size of rava, maida and things like that. Same thing is done in civil engineering laboratory to find out how much percentage of material is passing below, how much is retained. Okay. Yeah, and that curve, this this curve is something like this. This is the particle size, this is percentage passing. %, 20%, 30%, 20, 40, 60, 80 and 100. So you take this 50% and find out what is the diameter which is passing through. The curve is something like this, some kind of S-type curve. See, for example, if 45% of the particles are smaller than 2 mm and 60% of the particles are less than 4 mm, then D50 it is between 2 and 4 mm. That is for explanation only it is giving. For this 45% this is 2 mm and 60% it is 4 mm. This is based on one sieve analysis, because for 2 mm particle size they have found out what is the percentage passing. For this 4 mm they found out percentage passing. They say that this D50 size is between 2 and 4 mm. The point is, if you take a sand particle, the size of the sand particle may vary from 0.1 mm to 2 mm. If you take a sand, wherever it is, you take it to your laboratory, and if you want to find out the sizes of the particle, it may vary from 0.1 mm to 2 mm. Then you have to designate which particle size to be used for design analysis. What will you use, 0.1 mm or 2 mm? For some cases you can use 0.1 mm, for some analysis you can use 2 mm, but representative is the 50 size. D50 size means that 50% of the size of the particle will be below and 50% of the size of the particle will be above. That is what it says, it separates that. Similarly, when we design this Hudson's formula, the weight is W50. What we are designing based on the significant wave height, it is W50. It is based on weight, it is not by the size. When you want to place this weight, 25% should be in the range of 0.75 to 1 times W50 and 75% should be in the range more than W50. That is the wave height. See, we are designing for significant wave height, we are not designing for maximum wave height. When you design it for significant wave height, there is a possibility that 1/3 of the waves will be more than what you have designed for. To cater to that, we want 75% of the stones what you are using should be more than W50, only 25% should be less than W50. The minimum weight should be only 0.75. Generally the maximum weight should be 1.25, we do not recommend more than that. The another advantage of is, if you have this gradation, then only it will be well packed. The void ratio what we discussed will be about 30%. If you have uniform size, the void ratio will be 40% and all, it is not good for stability of the structure. For energy dissipation, about 30% is required. So this is what we are designing. So when you are using a formula, what you have to see is what you are getting from the formula mostly will be based on a statistical information. So now we will go to the design calculation. So we have to find out what is the significant wave height. I used 1.8. So I told the range for significant wave height is between 1.6 to 2. In some places we use 1.6, some places we use 1.8. Appropriate number is 1.8. If you use 1.6, it is more on a conservative side. Generally we use it for very shallow waters. So 3.47 meter is the significant wave height. Then we have what is known as the berm width. So when you talk about the breakwater, so you will have the breakwater will generally consist of like this. So this is called as the berm width. This is equal to 3.5 times significant wave height. Actually there is a range, this 3.5 hs is not a common parameter, it can vary maybe 3 to 4 hs or 3 to 5 times hs. So when you substitute hs in meters, you will get the berm width as 12.15 meters. Then we have to find out what should be the level of berm. The level of berm from the water level should be about 0.65 times hs. The idea behind that is the top of the wave will be about 0.5 hs. So this berm top will be higher than the top of the wave, that is why we want to put 0.65 hs. So this depth will be about 10.26 meters. Then next is we have to find out what will be the run up. Run up depends on a parameter called surf similarity parameter. You please memorize this formula. Surf similarity parameter is tan theta divided by root of hi by L0. What is the unit for theta? It is dimensionless. What is hi by L0? It is called as wave steepness. Okay. So we have to calculate the deep water wavelength. The limit is d by 0.5. Based on that you can get the L0 as 16. When d by L0 is equal to 0.5, L0 will be d by 0.5, that will be 16 meter, and the berm side slope, if you are assuming 1:1.5, this slope you assume 1:1.5, then you can substitute this value tan theta divided by hi by L0. This surf similarity parameter comes as 1.43. It is less than 2.5. This run up by hs is given as 1.43. So when the wave is coming, when it is going here, it goes and it runs up here and reaches this point. This point with reference to this level is called as r. This r by hs is about 1.43. This is given from some tables. So your this height will be about 5 meters. So you have to keep the crest above this level. So what we are giving is, we are keeping this level is giving a clearance of 0.5 meters. This depth is from this point, it is 8, 13, 13.5. This is what is given here, 13.5 meter. So now what we have completed is, we have fixed the slope, we have fixed the width of the berm, we have fixed the top level of the berm, we have fixed the top level of the breakwater. This is what we have done. The parameter which is used for all these purposes is hs, that is a significant wave height, which is used to fix all these parameters. Once you fix these parameters, then we have to use a formula to calculate diameter of the armor units. That formula is given by hs by delta into ns. This delta is nothing but Wr by Ww minus 1. There is a similarity between what we have done in the breakwater design, that is Sr minus 1 is nothing but delta. Hudson's formula and this are one and the same, only it is given a different kind of dimension. Wr is the unit weight of armor, Ww is unit weight of sea water. So you get delta which is 1.585. The stability number is the one which you have to get based on model studies. That is what we are doing in our wave flume. Most probably next week or we will be seeing that procedure how to get this stability coefficient. So you use this stability coefficient and calculate dn50, substituting Hs which is 3.47 SR minus 1 into stability number 1.7. These are numbers, this is having the unit of meter. So your dn50 will be 1.288 in the unit of meter. Then you have to calculate the individual armor unit stones. The weight of the stone is dn50 to the power of cube into Wr, which is about 5.66 tons. Suppose you are using not a Berm breakwater, some other type of breakwater, in that case this weight will be at least 3 times more, right, that is what we are discussing. So if you use a conventional breakwater, this weight will be about 18 tons. So by but the quantity of stone required in a Berm breakwater will be almost twice, because normal breakwater and Berm breakwater, if you see the quantity that is required, it will be almost twice, but the weight of the stone will be lesser, and getting a bigger size stone in a quarry is very difficult. So getting a 6 ton stone is very easy. Then we have to find out the armor thickness, that is given by this formula n into kd into d. The same formula can be used for normal breakwater also, where n is the number of layers, that is 2, that is to be assumed for stone. Kd is the layer coefficient, the layer coefficient depends on the armor type what you are using. It is given some standard textbook. There is a coastal protection manual by US Army of Corps, is available in the net also, you can get this value from that. So these values are available, but you memorize these values, you have to get these values, and then you calculate the armor thickness, that is about 3 meters, and the crest width also is a function of n into kd into d, where d is the size of the stone what we are using. The dn50 and d, this d and this dn50 are one and the same, 1.28. The number of stones width required is about 3. So what is required for design purpose is 4.5 meter, but we can provide slightly more also. So now what we are designing is, we are designing the armor. What we are designing, what we are, I have told is you should have at least 2 layers here, and you should have at least 3 here. It will not be like exactly like this, but some odd shapes it is preferable to keep this. The stone what we are using here is W50, that weight is about 6 tons. So the weight of the stones for under armor layer, that is the next layer which will come below this, there will be one more layer which will be coming below this. This is called as the under armor layer. This is varying between W by 10 to W by 15, that is given. Then we have the core layer. Here we will have the core, that is W by 100 to W by 4000. Wide variation is required because it will get packed and there will not be any sand particle moving from one side to another side. Then we have the bedding layer, which is 500 mm. The weight of the stone is 0.1 kg to 50 kg. The average size is about 30 kg. We are calculating the diameter of the stones also. Then we need a toe mount. Here earlier we have given some other formula, but here we are giving 3 times Kd into d. The Kd is nothing but this coefficient, layer coefficient, this K and Kd are one and the same. This layer coefficient is 1.15, so you can get 4.5 meter as the width and 3 meter is the height, that is 2 into Kd into d, where d is the dn50. What we are using here, d is nothing but this dn50 what you are calculating, which is 1.288 meter. So to summarize, what is required for the design purpose for the berm breakwater is the diameter of the individual armor unit, which is a function of Hs, delta and Ns. Hs is the wave climate for which you are designing, delta is the property of the armor units what you are using, Ns is a stability coefficient. The stability coefficient is having a wide range. So you can have a stability number of 1.7 or 3. If you use a stability coefficient of 3, your weight of the stone is 1 ton. If you use a stability coefficient of 1.7, the weight is 5.66. See, there is a design philosophy. We allow the breakwater to take a shape, some kind of a S shape. So we allow this to reshape itself like this. This is, it will take a shape. This reshaping is not done by artificially by us. The waves which are attacking the breakwater will take the reshaping. If you want to have the reshape, then you should use a higher stability coefficient, then the weight of the armor units will be less and then it will take a reshape. If you use 1.7, it is non-reshape, whatever you have put it will remain almost the same. There is advantage of using a reshape type breakwater because the waves which are attacking makes it compact and makes it alright. So you have to do a design procedure for this and accordingly design this, but if you want to be very conservative, you have to use a lower stability coefficient and non-reshape type of breakwater. So here we have give the comparison, the Hs will not change, the berm width will not change, berm level will not change, crest level will not change, the crest width will be reduced, but for construction purpose we will increase it to 8 meters. That is another important thing when you go for the civil engineering or harbor engineering design, there is a formula which gives the width. For construction purpose we have to revise it for construction as well as for maintenance. Then this armor layer and other thicknesses are given. This is for a design water depth of 8 meter and significant wave height of 3.47 meter. Similarly, you can get for different water depth and different wave height. Any doubts in this? No doubt. So this is the type of cross section what we finally will get. So this is the called as the toe mount height, this is the toe mount width, this is the slope of the breakwater, and this is your core layer, this is the under armor, I am sorry, this is the armor layer, this is under armor layer, then we have this core. Below the core we have this 50 centimeter of 500 mm of bedding layer. We assume this 500 mm will go below the seabed and we will have the 8 meter depth from here. I have marked this as mean sea level, but this level is depends on the tidal level and storm surge and other things what you have to consider. This is as per design purpose we need 4.5 meter, but anyhow for construction feasibility we may raise it to higher values. Similarly, the berm height also we may increase, because during construction when the waves are breaking the lorries have to move in this. So, this level, see, you will be first dumping the core, then you will be dumping the secondary armor, then you will be dumping the armor units. So, what they do is if we have the suppose this is your shoreline and you have one short breakwater, Gopalpur where we have the short breakwater, then we have the long breakwater. What they do is they start the construction from this point and then they go towards the end. They do not put the armor stone until they reach this point, then they will put the armor stone, then they will come back. Is it clear? Sometimes they may not even put the under armor layer, because if you put this armor stone your trucks will not move. See, your trucks are going and dumping the stones here. If you put bigger size stone, 6 ton stone and all, on top of 6 ton stones you cannot move your vehicle. That is one of the reason they do not put this armor. What they do is they go all the way there up and then come back. Since the wave heights are higher, as you go to deeper water they will start with +7 and they may go up to +8 meters, right. Your armor thickness in this case is about 3 meters in 8 meter water depth, whereas in 6 meter water depth the thickness required will be 2 meters. So, if you maintain this level as constant, the secondary armor level, this level should be slightly above the water level. See this top of the secondary armor, what is shown here, this is the top of the secondary armor. This level should be above the water level. As per the drawing it is not above, but this level should be above the water level. That is one of the practical consideration which you have to see. Even if that level is constant everywhere, in a deeper water the armor weight is high, armor stone size is high, so the top level also will be very high, and that is why they go in for differential level. This level is not uniform, this level will be increasing as you go. They will put some smaller size stones to make the trucks to go. It may not go, but they will pack it. But generally it is not desirable to pack the armors. If you place the armor, this dissipation will not take place, energy dissipation. See, actually they will see, we are discussing, I do not know why this mouse is not, see this is the point what we are discussing. We can put this layer as well as here, some this width also has to be increased. This width actually should be 8 meter, not this width. So, you can pack this area and the area here for enabling the truck to move. Through this distance, through this width the truck will go forward, through this width it may come back also. One of the advantage of the berm breakwater is you have a place to, one road width to go forward, another road width to go back to return, and this road width also is sufficient for going up and down. But if it is a conventional breakwater, they will be constructing some areas where the vehicle can turn around areas. Typically every 500 meters or 300 meters center to center they will have this turnarounds for the vehicle to go and turn and come back. These are all construction requirements what you have to do.
So this
It can be same or it can be different also. Generally we provide the same, but generally the slope above the berm is flatter compared to the slope below the berm, because the wave energy is concentrated only in the top region, not in the bottom region. We were discussing why it should not be packed here. So it is desirable not to pack this area, because when the waves are coming it will go over this and then run up over this. So all this phase it is preferable not to pack it. Whatever drawing they have shown is also not correct. It will not be like this, it will be like this or it will be like this. There will not be some small stones coming here and all. Armor stones will not be packed. We should have sufficient void ratio so that you can allow the wave energy to dissipate. There are other methods also to construct the breakwater. One is called as end-on construction, end-on method. Another is by barge dumping. Sometimes a combination of these two will be used, but it is preferred to use both the methods, end-on method as well as the barge dumping. Barge dumping means you transport all the material into a barge. It is a split barge which will open at the bottom. Suppose they have constructed up to this point, the barge will go and dump at the bottom. The core layer, the filter layer will be dumped by the barges as well as the tow mount, because it is very difficult to use a crane to dump it, but barge method of dumping is preferable. It is not cost effective, but it is very construction wise it is very what is called as robust, and you can get what you want to desire. What is desirable can be achieved by barge dumping, but as far as the end-on method is concerned, this can be used for some portion of core as well as under armor as well as primary armor layers, and you have to use some cranes to dump the stones. Suppose you calculate the width of the breakwater at the bottom, the width of the breakwater may be as high as 10 meters, 100 meters. From here to here the width may be 100 meters, because it is 8 meter into 1.5, that is around 20 meters. This is 12, 32, then here it may be around 6, 38, 42 and another 25. So it will be around 67 meters. Suppose your crane is moving on top of this, the crane should have a reach of about 30 meter to dump the tow mount. It is very, you see 30 meter is very very huge reach that a crane has to move and then dump it, and it is a very slow process also. So with this I complete this lecture on Berm breakwater.